Welcome back to Delta G Chemistry Videos, Episode 2. Today I'll be doing an acid-base extraction of a carboxylic acid. I just want to break down the chemistry real quick. So I ran this reaction, this oxidation on this diol that gives this hydroxy acid, which is a pretty cool reaction. So the reaction doesn't go to completion. So I have a mixture of diol to carboxylic acid, and there's a really great way to separate these two compounds without having to do column chromatography. So just a quick diagram. The diol and the carboxylic acid partition into the organic layer in my separatory funnel. However, now basifying, now the carboxylic acid is deprotonated, rendering it polar and partitioning into the aqueous layer. Decanting off the ether layer with the diol removes the diol from the mixture. Acidifying the aqueous layer protonates the carboxylic acid and effectively moves it into the organic layer, which can then be decanted. And now I have two separate flasks containing diol and carboxylic acid. So let's see how this looks inside the lab. So the first thing you do anytime before you add anything to a separatory funnel or a vessel that has a stopcock is you add a little bit of solvent to make sure that the stopcock is actually going to seal. Otherwise, you could have leakage or drippage from a loose stopcock. So first I'm just going to rinse the reaction into the separatory funnel. I'm going to use some diethyl ether and a little bit of water. So after I've sufficiently rinsed the reaction vessel with ether and water into the separatory funnel, I'm going to go ahead and add about 3 milliliters of 1 molar sodium hydroxide, and I'm going to go ahead and give the separatory funnel a shake. Notice how when I'm shaking it, I am going to vent the separatory funnel. There is some evolution of gas that comes out. So, and make sure that you're pointing the end of the separatory funnel that's letting the gas out away from you, so you're not covered in the splatter. Make sure that you rinse the top of the separatory funnel with ether or water or whatever organic solvent you're using back into the separatory funnel. That makes sure everything stays in the funnel. This process takes a little bit of time, but now just wait for the layers to separate. Sometimes it's hard to see if the layers are separated, so you can go ahead and give the separatory funnel a swirl. That'll help kind of separate the breakup and emulsion and separate the aqueous and the organic layer. Now just wait for the layers to become separated. You can put your hand behind the separatory funnel. I think this is a good visual. It gives some good contrast to see between the two layers, and then go ahead and start draining out the aqueous layer out the bottom of the separatory funnel. So I'm going to go ahead and test the pH right now just to make sure that the aqueous layer is sufficiently basic enough. So just going to pull in a tiny little aliquot and spot it on some pH paper. So the pKa of a carboxylic acid for benzoic acid, for example, is 4.2. The pKa of ethanoic acid is 4.7. So taking that into account, the pH of the 1 molar NaOH solution that I'm using is about pH 14. So that's sufficiently basic enough to deprotonate the carboxylic acid, rendering it polar and now going into our aqueous layer. So I'm going to again perform another extraction. So again, vigorously shaking the separatory funnel. That way the ether layer and the water layer are mixing, and all the carboxylic acid is starting to partition into the aqueous layer during our separation. So if you spin the separatory funnel, that can help separate the phases a little better. It's conical, so it's really nice to vortex that way. Here you can see a nice visual that yes, indeed, you are getting separation. So now that the layers are separated, I'm going to decant off the aqueous layer by draining it out the bottom of the separatory funnel once again. Typically, you want to perform these extractions about 3 times. That's because of the partition coefficient. I'm not going to go into the math there, but yeah, about 3 to 5 times is a perfect amount for extractions. So one point of contention that has been an ongoing discussion in the lab is, should you be pouring out the top layer out the top of the separatory funnel or drain it from the bottom? I prefer to pour the organic, in this case, out the top of the separatory funnel. But whatever preference you have is obviously up to you. Um, this is just how I do it. And my reasoning is that the top of the separatory funnel is theoretically clean. No water has passed through it. So that's why I typically pour the second layer out the top of the separatory funnel. Okay, so now to perform the second half of this extraction, I have to acidify the aqueous layer that's about pH 14 right now to something below pH 4. So to do that, I'm going to use a 1 normal HCl solution, and I'm going to just keep adding in HCl, uh, the aqueous HCl, in increments until the solution becomes acidic, and I'll be checking that with pH paper. The pH paper should turn red when the pH has sufficiently become acidic. So I'll be monitoring that slowly. You don't want to go ahead and just dump a bunch of HCl into the solution. You want to slowly titrate, if you will, in the HCl acid. So once you've checked that the pH of the aqueous layer is sufficiently acidic, you can go ahead, I'm going to go ahead and add diethyl ether on top, and then I'm going to vigorously shake this acidic aqueous solution. Now the carboxylic acid should be protonated, and it should partition into the organic layer of this mixture. So I had been repeatedly adding HCl to this mixture. You can see that I was taking little aliquots of the aqueous layer, and I was spotting it on pH paper until I saw the spot turn red. At this point now, I'm going to extract out the aqueous layer, and then I'm going to pour the organic layer out of the top of the separatory funnel into a separate flask, and this should have my carboxylic acid in it, but some of the acid still may be present in the aqueous layer, so I'm going to re-extract it again up to 3 times again, just to make sure that all the carboxylic acid has been removed from the solution. And there I am again, just checking, double confirmation to make sure that the aqueous layer is still indeed acidic. So I'm going to perform another extraction here. Just going to re-pour the aqueous layer back into the separatory funnel and add some clean, fresh diethyl ether on top. Then going to vigorously shake the separatory one more time, just making sure that I'm extracting all the carboxylic acid out of the aqueous solution. So how can you tell if you've sufficiently extracted your carboxylic acid out of the organic layer and separated the two compounds? So here in the left-hand corner of the screen, you can see a TLC plate. This is of the reaction mixture and the diol, so you can see that I've co-spotted the reaction mixture in the middle. The most polar spot is the carboxylic acid, and the spot on the furthest lane to the left is diol. So this is what the reaction mixture looks like, and so let's see how the TLC looks like after the extraction. So to check the efficiency of the separation, I'll go ahead and TLC the first organic layer that I collected against the second organic layer that I have just collected now versus the now acidified aqueous layer. And you can see that the diol has definitely separated into the first organic layer. The carboxylic acid is in the second organic layer, and there's virtually nothing in the aqueous layer. So from here, I'm really confident that I've extracted everything out of the aqueous layer, and that I have indeed separated diol from carboxylic acid without the use of flash chromatography, which is really awesome because anytime you don't have to run a flash column, there is steps saved and yields are typically improved. So the last thing, now that I've separated these two compounds from each other, is I'm going to go ahead and dry the solvent. So what that means is that I'm going to wash the organic layer that has my carboxylic acid with saturated brine solution, saturated sodium chloride. And what that does is any residual water that's in the diethyl ether solution should be removed and partitioned into the aqueous layer, thus removing any water particulates from my diethyl ether solution. And that TLC plate that's running right there is the TLC that you've just seen of the two organic layers plus the aqueous layer. So always double check by TLC to make sure that you've extracted your compound out. And another word of advice is to never throw out your organic layer or your aqueous layer until you're absolutely 100% confident that you have isolated your compound, your product, your recovered starting material, or anything. So even though I went ahead and dried the organic layer with some brine in a wash, I'm still going to add some sodium sulfate. This will collect any other residual water and make sure that the diethyl ether layer completely has no water in it. And the idea is you want the sodium sulfate to be free flowing, so you can see that it's flowing from side to side and it's not clumping or sticking at the bottom. This is the sign of that the sodium sulfate has absorbed all the water in the solution. Typically you have to wait for about 15 minutes for the sodium sulfate to absorb all the water content. Now I'm just going to go ahead and filter this solution. I have a small piece of glass wool at the bottom of this filter funnel, so it makes sure that any of the sodium sulfate that kind of falls into the flask doesn't go into my round bottom flask. So I concentrated what was in the round bottom flask and I transferred it to a small vial, and then I'm now concentrating it on the rotovap so you can see that it's evaporating. And since it's diethyl ether, you don't want to pull too much solvent or pull too much vacuum, or else the solution could bump into the bump trap or boil into the bump trap. So yeah, get to see what the hard work has paid off. And there it is, a beautiful white solid. That's what the carboxylic acid looks like after the end of the reaction. Beautiful white powder. If you like this content, please leave a like. And if you have any ideas, suggestions, please comment below. Until then, thank you very much for tuning into the channel. Delta G Chemistry Videos.